Hello and welcome back to the MCAT grind. We have Physics Chapter 4 about fluids, and fluids is one of the questions that will likely become a whole passage, or you will see it at least once in a discrete question. So because of his huge percentage on the MCAT physics section, you will definitely see at least one question or two on the fluid part. Speculating it will probably be one about the composition of or the percentage of fluid of the object being sunk into the fluid, and perhaps one demonstrating using Bernoulli's equation. Now, starting off, we want to talk about density. Basically, density, rho, is by mass over volume, how dense something is, how much matter it is within that finite space and volume. Now, that can be put into that force equation we have before. Force equals ma, but we replace m with rho times volume. So we have rho volume times g. That's the weight of the object inside the fluid and liquid. We can use that to determine how much of it weighs. Now, the density of water is 1,000 kilograms per meter cubed. It can also be 1 gram over cm cube. To find the density of a substance, you can use that relative to water to find the specific gravity. Now, the specific gravity of an object, let's say, is 2,000, and since the specific gravity and rho of water is 1,000, then that object has 2,000 rho as its density. Now, the object will obviously sink. But if it's less, the density is less than water, what's going to do? It's going to float, of course. Well, how much is it submerged? Well, the submerged percentage is calculated by the density of that substance divided by water, and that is a percent. So ice is about 0.92 specific gravity. So divided by 1 of water, that would be 92%. So 92% of ice should sink below the water. So you hear the saying, most of the iceberg is underneath the water, right? So if it balances out the weight of the object plus the buoyant force pushing up, then the object will stay in that state and will not sink or float. It will just stay in that same place. Okay, so we want to talk about pressure. The pressure is determined by force divided by area. That can also be denoted in different forms. So force is the force pushing down either from gravity or from buoyant force pushing up. We also have this F1 D1 equals F2 D2. That's experiencing two pistons, right? If you were to push down a thinner piston, then you can push up a much larger piston over a huge surface area because you're moving through a shorter amount of distance. By pushing down that one specific long piston with a small surface area, you can push up a much larger object with more force, but you can only push it up a small area. But that's still lifting it up, right? Now, we also have the continuity equation from A1, which is the area, this cross-sectional area of the tube at place 1 multiplied by its speed of the fluid, and that should equal to A2 V2. The buoyancy of an object, if the force of that is equal to the force of gravity of like this weight on down, it's going to float. But if the weight is much bigger than the buoyant force of the liquid pushing it up, then the object is going to sink. You can think of how much water or how much liquid has been displaced as the buoyant force. The buoyant force will equal the amount of object being displaced. So if you have an object and you're holding it by a string, that string will say, oh, this object weighs 5 newtons, for instance. And when you dip it in water, boop, it's going to get pushed up, and now the scale says, oh, the object weighs 2 newtons now. So you know the buoyant force is that difference of 3 newtons, right? But the overall weight of the object is 5 newtons, so when you let go of the string, there's still a difference of 2 newtons, so that's going to slowly sink to the bottom. Great, now we have the Bernoulli's equation, which is the absolute pressure plus the pressure experienced by the speed, the velocity segment, and also by the height. These are all different pressures from different factors. Now, it's saying that all 3 of these combined will be constant as it moves through a tube. So from one side to another, if it goes from an area with a much larger section area and goes to a much smaller section area, the velocity will have to go faster here to fit all that liquid. In order to stay constant, according to Bernoulli's principle, then the pressure here will, the absolute pressure here will be smaller. And since the outside is exposed to the same atmospheric pressure, the same atmospheric pressure will push down the fluid a lot more here. This is called the Venturi effect. Venturi, Venturi effect. Since here, absolute pressure, P, goes down due to the velocity moving up here. Note that the height remains constant because they're both at the same height, not the liquid, right? Just the tube, from experiencing the effect of the absolute pressure. And the gauge pressure change here. Gauge pressure, G-A-U-G-E, gauge, is just the difference between the outside versus the inside pressure. Okay. Now, Poisson's law talks about laminar and turbulent flow. As an object moves through a liquid, whether it's air or water or anything fluid, it's going to move around it, the liquid, and the fluid is going to move around the object if it's moving at normal speed. But if it moves super fast and past a critical speed, critical velocity, then it's going to experience turbulent flow, which goes like whoosh, 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 whoosh. Right? If it's slow, it's just laminar flow, slowly shooting through it so it can let it fly through the air. But if you throw it so fast, then it's going to get resisted by the airflow and going to make it do all funny things. Alright? So, according to Poisson's law, the flow equation equals to pi the radius to the power of 4 times the difference in pressure divided by 8 times, this is viscosity. This little n is viscosity times the length. That describes the flow of the object through that media of fluid. And this is the critical velocity at which it turns from laminar flow to turbulent flow because it's moving through the fluid way too fast. So this talks about Reynolds number, NR, Reynolds number. This is viscosity, and this is the density of the fluid times the diameter of the fluid it's containing in, or the diameter of the object. Now, this describes turbulent flow or laminar flow within a tube, so it may be within what is containment. If the viscosity of the fluid is greater, the greater it is, such as water, then you may have a larger, what's it called? Critical velocity. But if it's through something with a lot less viscosity, lossless viscosity, such as vacuum, for instance, it's going to experience laminar flow a lot better. But obviously, vacuum has not much fluid in it. So think of the difference between moving through water versus moving through honey. Okay, in water there's more particles going around, so a lot less velocities, a lot less viscosity. So the velocity critical at which it's going to experience turbulent flow is much faster, or sooner, right? Because a lower velocity, critical velocity, to hit that turbulent flow. And the density of it will also matter. Alright, So that's pretty much it for fluids. Good luck.